previously, when we were looking at Coulomb's law, we had considered a spherical volume charge, but we only looked at the electric field due to that volume charge outside of the sphere. So in this example, we're going to come back and we're going to say, what do we do to characterize the electric field inside and outside of the sphere? And so we're going to do that with Gauss's law. So we want to determine our electric field everywhere due to this charge distribution that has spherical symmetry and charge density given by this equation. So we have rho of v has two components. For our lowercase r, which is our radial distance from the origin, less than capital R, which is the radius of the sphere, we're given that our charge density is rho naught times lowercase r divided by uppercase r. And then if our radial distance is greater than the sphere, the radius of the sphere, we have zero charge density. So basically we're saying we have a sphere which has this much charge density inside, and we see that it is only dependent on r, so our other two things are just constants. And so what that means is even though we don't have a uniform distribution like we've seen in the previous examples with Gauss's law, we do still have symmetry. So we have radial symmetry or spherical symmetry in this case. Okay, so as always, I would encourage you to pause the video and try to set this up or work through it yourself first, and then come back to the video for the solution. So in this case, what we want to do is we actually want to define two Gaussian surfaces. One of them is going to be inside the sphere, and one of them is going to be outside the sphere. So we're going to define two Gaussian surfaces, both of them spheres. So one of our Gaussian surfaces is going to have a radius which is less than our uppercase r. So remember, our uppercase r is the radius of our sphere, and then we're going to have another surface with a radius greater than r. Okay, so let's look at these sort of one case at a time. Let's start with the case of our r is less than our radius of our sphere r. And so I know that's kind of, I'm saying radius of various spheres. So remember, we have some physical sphere that has some charge density characterized by this, and then we have our Gaussian sphere, which is just a mathematical surface. So if we're inside our physical sphere with our Gaussian sphere, again, kind of confusing, what we're going to have is we're going to have, from our Gauss's law, that the surface integral of E dot ds, and so I'm going to rewrite this a little bit differently. So instead of E, I'm going to write it as epsilon times, instead of D, I'm going to write epsilon times E, and I can pull out the epsilon since that's just our permittivity of free space. So I can say epsilon naught times the surface integral over the closed surface of E dot ds. So we know that is equal to Q enclosed from Gauss's law. And so our Q enclosed is going to be the integral over the volume of rho v dv. Okay, so let's start by evaluating this integral. We're going to come back and evaluate that other volume integral in a minute, and then we're just going to equate the two. So this is going to be the integral over our surface E dot ds. We know that our electric field is only going to be in the radial direction, and our ds for the sphere is going to be in the r direction as well. So we can just pull that, our electric field term out, so we can say epsilon naught ER. So that's essentially the same thing as we were saying before about our d is constant on the Gaussian surface, and we have the integral over our closed surface ds. And so this gives us epsilon naught ER 4 pi r squared, as we've seen before. Okay, so that's our first integral. Now we want to evaluate this second volume integral. So we can say the integral over the volume of rho v dv. So that's going to be the integral as r goes from 0 to lowercase r. So that is where we're setting the radius of our Gaussian surface. And our theta is going from 0 to pi. And our phi is going from 0 to 2 pi. And we're integrating our volume charge density. And our dv for spherical coordinates is r sine theta d phi d theta dr. So all of that is our dv. Well, we can sort of separate here our terms. So we have the integral from phi. There's no phi dependence anywhere, so that's going to give us a 2 pi. We have only the sine theta d theta. So integrating from 0 to pi, that's going to give us 2. So this is going to reduce to the integral from 0 to r of rho naught r over capital R. So that's our equation for our charge distribution or our charge density. And then we have 4 pi from our two integrals for theta and phi, and then we have the r squared from the dv still hanging around, and dr. So we get the r cubed term, so that 4 is going to go away when we integrate, and we're going to have rho naught pi r to the fourth over capital R. Okay, so now what we're going to want to do is equate these two terms here because both of those are equal to the charge enclosed. And so equating those two integrals, we get epsilon naught ER times 4 pi r squared is equal to rho naught pi r to the fourth over capital R. So we see the pi terms cancel out. Our r squared is going to take out two of these guys, so we're left with r squared here. And ultimately what we're going to get is that our electric field in that region is going to be equal to rho naught r squared divided by 4 epsilon naught r in our r direction. And again, keep in mind, our uppercase r here is the radius of our physical sphere, and our lowercase r here is the distance from the origin inside of that physical sphere. So that's our electric field inside the sphere. So now we can say, well, what about outside the sphere? So we set the radius for our Gaussian surface greater than the radius for our physical surface, and we basically just redo that same process. So we're going to start by, we just copy this so we're not writing it down. So we're going to start by saying we have some surface integral of E dot ds, and again it's really D dot ds, but we've taken this epsilon naught term out. We know by Gauss's law that's equal to charge enclosed. We know our charge enclosed is also equal to this volume integral. So the first term isn't going to change at all. So we're still going to have for this term our epsilon naught ER, because we know that's only in the r direction, times 4 pi r squared. So same process as we went through above. Now our volume integral, on the other hand, is going to change a little bit. So we're going to have the integral over the volume of rho v dv, and so this is going to be equal to the integral from r equals 0 to r, the radius of our Gaussian surface, and then we have the integral from theta equals 0 to pi, phi from 0 to 2 pi of our rho v r squared sine theta d phi d theta dr. So all of that last bit was our dv, of course. And so now when we're integrating across r, so we're going to get the same result. We're going to have some integral of something times our 4 pi r squared dr. So these terms come from our sine theta d phi. And what we can see, though, is now that our Gaussian surface is outside the sphere, we're going to have two integrals. We're going to have one from 0 to capital R, and then once we get past that, we're going to be in this area where our charge density has changed. So we're going to set up our first integral as an integral from R goes from 0 to uppercase R, so that's basically going from the origin to the surface of our physical sphere, and our charge density in that entire region is going to be rho naught R divided by capital R, and then we have plus the integral from capital R to the radius of our Gaussian sphere, and so in that region our charge density is 0. And so 4 pi r squared dr, of course this is going to go to 0, and we're just going to be left with this first term, which is going to give us pi rho naught r cubed. Okay, so now the same process, we're going to equate our two integrals because we know that both of those are equal to our charge enclosed. So if we do that, we get our epsilon naught ER 4 pi r squared is equal to pi rho naught r cubed. Again, our pi terms are going to cancel out, but that's it this time, so we can say our E is only in our r direction, so our total E is equal to ER, which is rho naught r cubed divided by 4 epsilon naught r squared in our r direction. So now all we need to do is sort of combine those two pieces together to get our overall electric field. So our overall electric field is going to be equal to, from the first part, we said for our inner Gaussian surface, we have rho naught lowercase r squared over 4 epsilon naught r in our r direction. And so that was for the case of r less than the radius capital R of our physical sphere. And if we're outside of our physical sphere, our electric field becomes rho naught capital R cubed divided by 4 epsilon naught lowercase r squared in our r direction. And so that's for r greater than the radius of our physical sphere. And so this would be our final answer here. And so I know this is maybe a little bit difficult to interpret, but of course you can imagine substituting in, for instance, a number for our capital R. So perhaps it has a radius of 2, so we'd plug in 2, and of course we could have some constant value for this rho naught. And then we can sort of start to see the dependence here. So inside our sphere, we're going to be, our electric field is increasing as we approach the surface, and then as we approach the surface and leave, our electric field is going to be decreasing as r squared as we get away from that surface. So now we sort of know how to characterize our electric field everywhere for the sphere. You can look on pages 137 and 138 in the textbook for a similar example. The only difference is there is a uniform charge density in the sphere. So a little more simple, maybe a little less confusing in terms of all of these r's floating around as well.